Kathmandu Nepal. I'm very pleased to have all the hospitality and welcoming. Thank you very much. Let me start with the first talk. But before that, I'd like to introduce my co-chair, Monica Ta, and rapporteur, Rito. So three of us will design this session. Thank you. First speaker will be Professor Mary Hubbard and others, titled Cross Faults in the Himalaya, their topographic and structural expression.
It looks like we are unable to have the slides in the middle. So if you get tired of listening to me, you can read the poster in the middle section there. So my name is Mary Hubbard. I'm a retired professor from Montana State University. I've worked in Nepal many. Thank you for having me back in Nepal and for coming to attend this session. I'm going to talk today about cross faults in the Himalaya. So what do we see in the topography? What do we see in the rocks themselves related to cross faults? So I want to thank my co-authors here, but many others have also worked on this. So I've got special thanks to Malay Mukul, who's here in the audience, Vinny Srivastava, faculty member in Bhopal, India, but also then graduate students who have worked, done a lot of the field work that relates to what I'm going to present today. So we all know are very familiar with kind of how the Himalaya were formed with the India-Asia collision. But what I want to just say with this, let me find it. I can't point to the middle and I can't point to that far slide. But on this map of the Himalaya that originated from one of Ganser's original maps and has been used by many others, but we see the major thrust faults, and the trace of those faults are parallel or subparallel to the range itself. The cross faults we're going to talk about transect the range or go across the range are at high angle to the range itself or to those major thrust fault traces. But to give a little background on why I think that cross faults are important and that we need to know and understand these structures more, I'm going to go back 10 years to the 2015 earthquake, which we'll hear more about earthquakes, I should say. And what I'm showing here are this map of the aftershock data for about a year's period after the main events. And what was pointed out by the geophysicists who did work on this at the time was that in particular on the eastern edge, there's a very sharp boundary in the map pattern of where those aftershocks end. And it was proposed by the geophysicists that perhaps there's a fault of some sort that blocked the lateral propagation eastward. There are some interesting features actually off to the west as well in the 3 dimensions of these aftershocks. But I'm going to focus here on the eastern end that's so abrupt and easy for you to view on this image. In cross-section view, so if we had a cross-section that went right through this from northwest down to southeast, we see this in 3 dimensions. The scale here goes 0 to 20. But what we see is that sharp boundary is actually an inclined plane, and it projects up to an area that was previously identified by a topographic lineament that was known as the Gauri-Shankar lineament for many years, several decades actually. But that's approximately where it projects up to on the surface. These events are all largely 10 to 20 kilometers in depth. But I'm going to go back again in time to my first experience with a cross fault, and this was in 2016 when I returned to the Himalaya after several decades away from this part of the world. And I went back into the Khumbu. So this is the Dudh Kosi River Valley that goes up to Sagarmatha here in the upper part of this Google Earth image. But when I went back, and when I had worked there in the 80s, we didn't have Google Earth. And so it's such a It's such a luxury now to have Google Earth imagery. And when I went to kind of look at an area I was interested in this red box, this is an enlargement of that area, I saw these linear topographic features that to me looked like crossfault, or looked like fault scarps or some kind of a fault signature. So I went back in 2017 with a graduate student, and we were able to confirm that, yes, indeed, there are fault segments there that go through. So again, this is the Kosi River coming down. There's a little town of Bangkar right in here, a little village. So hence we've named this system now the Bangkar Fault System. So following that kind of confirmation of it being a fault, a master's student, Neil Seifert, went in and mapped in more detail. And so this is a map then of that Khumbu area. Here's Namche Bazaar and Lukla. Just for reference, Sagarmatha would be this small triangle up here. The South Tibetan detachment, I guess, roughly, well, outlined here. Some of the faults up here, anyway, surrounding Sagarmatha. The area between these two purpley colored lines is where Neil Seifert was able to find strands of this fault. So it's non-penetrative deformation, so multiple fault strands, and they were all within these boundaries. They're northeast striking, and we're in the greater Himalayan sequence here. And the structures that we identified in the field and then in thin section showed that this deformation along the northeast striking surfaces was a brittle ductile in nature. In thin section here, right where the camera shadow is zones of concentrated sillimanite, and it appears that that's where the deformation was focused, not so much in the quartz layers. Hence our thought that this is a little bit cooler temperature deformation. In some places, so in the background of this image here, we're looking southwest here, but there's a beautiful dip slope of this cross-fault structure here in this photo. For the kinematics that we could get from thin sections and from outcrops suggests a normal and dextral sense of shear, so an oblique motion on this cross structure. So just a nice photo of one of the strands. This is the peak of Taboche. So Taboche is northeast of Namche, and we're looking to the northeast here, and you can see this beautiful shear zone that comes right down here. This is a Luca granite here, and I think that the reason that that zone of deformation widens to the north is that these structures are wrapping around some of the Luca granite features up in the northern part of the Khumbu, such as this one coming down off the edge of the Luca granite. With a little delay during the COVID time, just following that, my PhD student Vivek Giri from here in Nepal was able to take that structure, so here are the same purple lines I showed in that last image. He was able to follow that structure to the south down through the Okhaldunga area. And again, he found multiple fault strands. Some of them had different senses of shear, but they were largely brittle structures. So this is a wide zone of fault gouge. This was also very brittle, shattered, and in one case, a very sharp contact between two lithologies. This is one of the granites in the area, and then a biotite gneiss here just adjacent to it, juxtaposed. So over time, we've identified other of these features, these cross-fault features, I will say possible cross-fault features to investigate. And I just want to point out here in the east in Sikkim is the Gish structure that Malay Mukul has worked on for many years now. Originally starting down on this reentrant of the range front, but finding that a cross-fault coincided or spatially was co-located with that reentrant. More recently, he's been working in this Kosi area, and we'll hear more about that as I understand. And he and I talked about possibly a crossfault going north from that or northeast. So we're going to take a look at this area up here in the Kathmandu area where I had a chance to explore a little bit more about that structure. Here's the Bangkar that we just looked at. We talked about the eastern edge of the fault, the aftershock data corresponding with Gauri Shankar. We'll end up here in Kathmandu. But so just going now up to the Kanchenjunga area. The peak of Kanchenjunga is just to the east of this slide, and the little yellow dashed line was my route trekking up and over, but trying to sort of chase this topographic lineament that came down through here. And there actually are several sub-parallel features in there as well. Just two photos in the northern edge, so here and looking to the southeast, you can see some of the, mostly just fractures. We weren't able to identify a lot of displacement on these features, but I think that's what's partly responsible for the topography in this area. Down to the south, so in the south of the area that I covered, a much more clear, again, very brittle deformation in this crossfall northeast striking orientation. Okay, just coming back to the Kathmandu Valley. So this is Kathmandu. You are here somewhere. And the two images right and left are the same, but I left this one on the left side sort of unadulterated, not modified, so that you can see some of these northeast, southwest striking features. And you'll notice if you go back to Stecklin's map, some of the other early maps, these features are marked on there as faults. So presumably they saw fault fabric there. But we've spent some time in here looking at some of these features south of Kathmandu. And the next slide we will look at the Kulakani area. This is Kulakani Dam is just in here. This is a waterfall that's just on the south side of Kulakani Reservoir. And in this waterfall, you can see, I think you can see some of the fault coming down in here. There's actually more faulting right there underneath the waterfall itself. What I like about this slide and this example is that it's very clear that the valley that you see here coincides with where the fault is. And so I'd like to make a correlation between some of these cross faults and some of our north-south valleys or other topographic lineaments that we see in Nepal. We get topographic lineaments from a variety of causes, but I want to say here that I think some of it has to do with faulting, and we need to look carefully in these areas. Okay, we're going to move now to the Malamshi area to the north of the Kathmandu Valley. So the Malamshi Valley kind of is to the east of Kathmandu. So to orient you, there's a tiny bit of the Kathmandu Valley shown in the lower part of this. Again, this is a Google Earth image. Malamshi Bazaar is here. Malamshi Gaon, a small village up in here where there was a landslide that played a role in the 2021 massive flood that came down that valley. So we're gonna start by going up into this area in the north, particularly in the area of the white box. And here you see it blown up a little bit more. So the village of Malamshi Gaon sits right up in here, right here in this little light spot. But then below it is the landslide. And so I think this is maybe an older image, but you can see the white kind of scar on the hillside, and I'm sorry for those of you in the back, it's probably coming out pretty small. But the other thing I want to point out is how straight this segment of the valley is in kind of a north-south orientation, and I would argue it's actually straight all the way down to here, and whether this is a landslide or something else that's pushed the river eastward in that location. But we were actually just up there in the last 2 days looking at some of the structure related to this. And so in that northern area, this is an oblique Google image, so hopefully you're kind of getting the sense here. You're looking obliquely at a village called Nakote. Malamshi Gaon would be just off this photo. But here we are looking at a part of that really straight valley or river section in the northern part. And in particular, you can see the gorge that the river is within, very straight cliff sides here. The photos, there's a small suspension bridge. I'm not seeing it, so you're not going to see it. It's right up in here. And standing on that bridge looking southward is this photo here. So again, you can see some of these fractures that go straight south down that valley. When you look in close at this rock exposure here, you can actually see penetrative fault fabric that goes through there. Turning around and looking to the north from that suspension bridge, again we see those fractures continuing northward. The point I want to make here is that I think cross faults not only relate to the earthquake hazard, and maybe the earthquake hazard in somewhat of a positive way if they limit lateral rupture, but they relate to the landslide hazard, I think, in a big way, and I'll say in a negative way for all of us, because I think they can enhance the landslide hazard. So again, here we're looking, the town of Malamshigal is up on the bank up here. Here's the big landslide that was reactivated during initial flooding in 2021. And that landslide went down, dammed this valley for a period of time, and when that let loose, that's when we got the massive flooding that happened in the Malamshi Valley. So I think some of you have probably been over there and seen that damage. Again, here's just that close-up of some of the rock that has the penetrative fault fabric that goes through there. We did look at a place in the southern part of the Malamshi Valley. Also, this is just like 2 days ago. So here's Malamshi Bazaar and an outcrop that's just down here, just off the road that comes over from Kathmandu. And there we found about a 60-meter wide gouge and brittle deformation zone with, again, very much a north-south strike. So ranging from north 10 west or to north 10 east, something like that, but generally kind of a north-south strike. And again, you'll notice that that segment of the river valley is also quite straight. And this zone right there would have nothing to do with that big flood, just because it's below the, where the flooding originated.
We have 3 minutes.
Okay, thank you. Okay, so I'm just going to wrap up with that and just say that I think many of our north-south topographic features correspond to these faults. Our topographic features correspond to these faults. They seem to be largely brittle, or in some cases maybe brittle ductile. They seem to occur as fault relays, so stepovers or zones of deformation. And as I pointed out with the earthquake epicenters, they may bound areas of lateral fault rupture. And I think they enhance the landslide risk and therefore merit more study in terms of being able to locate where they are, when they moved, how much they've moved, and so on. So with that, I'll conclude and thank you.
Thank you very much, Howard. I think we have time for a few questions.
Professor, I have 2 questions. One thing is that what is the significance of cross faults in terms of tectonics in Himalaya? My first question. And another thing is that we have seen that there is a very wide range of elevation when we start from the north to the south. So what is the difference between what we call the braided river system and the cross fault as you are indicating? So what I'm saying is that is this geomorphological evolution directly related with that braided river system, or it is actually the cross faults?
Yeah, good question. 2 good questions. Because of the theme of this conference, I didn't emphasize. Godin has written a fair bit about this recently, in the last 10 years, that's recent for some of us. And his idea is that some of the topography on the downgoing Indian slab, I'll say paleotopography, meaning structures, the ridges, are influencing the overlying rocks and causing these cross faults or related to cross faults. There's a possibility there is some lateral extension on the range itself. So, and there's extension, of course, lots of extension to the north in Tibet. And that extension could propagate down across the Himalaya. It probably should. And so maybe these cross faults relate to some of that extension. Again, I think we need to first really map these faults and understand them and when they moved and so on to understand the tectonic point. And then your second question.
Well, related to the geomorphology, like
Yeah, okay, and I don't know if that's a chicken or egg question in terms of, did the faults exist and therefore drainage favored that area because the rocks would erode? I guess the chicken and the egg, I don't know about the other way around. I'm not sure that you would have a valley and therefore create the faults. But yes, likely the rocks are weakened and so that's a favorable place to erode.
Thank you very much. We can move on now. More questions?
There are several, but yeah, you can catch me later too.
Yeah, please do so.
Yeah,
Yeah. Just one more.
okay.
Yeah.
Oh,
Cross-fault influence, seismic hazard potential in Himalaya.
okay. Well, so that was sort of what I tried to explain. In terms of the seismicity, if you've got a fault and the fault, there's some resistance in the fault or you're changing the rock fabric, that lateral propagation of the thrust fault that caused the big earthquakes may hit that and actually stop the rupture. So that's possible seismic connection. And the topography, I guess we were just discussing that if you break the rocks in a brittle fault zone, those rocks are weak and they're easily eroded, so then you get a topographic feature coinciding with the fault zone.
Thank you. We'll move on. And
You want
my
one
co-chair, Monica, will give a second.
one question.
Of this geological. So you are explaining about the cross fault, and you explain about 10-meter wide gulf zone, and
Yeah.
that may dam the dam the propagation of the shear wave of the seismic wave. Yeah.
No. So the connection I was making would be that the lateral rupture and fracturing related to the thrust fault movement, as it propagated, maybe hit a change in lithology or something that kept it from further.
It's not going to dam the shear wave. No.
That's a question for the geophysicist. Laurent will be speaking, is it tomorrow or later today? Anyway, you'll go to his talk.
Okay, it is so. It's very deep focused earthquake. It's very deep, maybe 100 kilometers down. How it can work like that? Because the fault cannot be go like this to the 100 kilometers down. The earthquake focus is too deep.
Actually, there have been earthquakes around, 50 kilometers deep that have had a strike slip sense that coincide with these cross faults. So they may go deep, which would favor Laurent, his model. But we should probably go
Sorry
on.
for the interruption. We are running behind the time.
Yeah.
We can take a coffee break.
One
because
more
we have
little
time
question.
to time during
I'm
coffee
going
break.
to hand this to the convener to
Thank you.
move, yeah.
Okay, everyone, well, presentation and question and answer concluded in that. And next presenter is Vasant Pota. The title of his talk is Stratigraphic Analysis and Correlation of Climate Periods in the Lesser Himalaya and Central Nepal. The floor is yours, Vasant.
I'm Vasu Developer, PhD, Central Department of Geology. And today's my topic says stratigraphic analysis and correlation of carbon units in the Lesser Himalaya, Central Nepal and Western Nepal. The presentation outlines introduction, research gap, objective, methodology, result, and discussion on implementation. This is the introduction. My study is focused on the Central Nepal Maliki area and Alpha Sindra section. So this section contains carbonate bands in the autochthonous successions, and there is the stratigraphy developed by the different researchers in the Central Nepal, West Central Nepal. So mainly the stratigraphy is sequence of the carbonate succession and the divisional environment of the carbonate rocks are not confined at that time, and there is no any detailed study of the stomacularis. There we see type sections, and the question arises is that studied classification of carbonate rocks in the lesser Himalaya is not confirmed in heavy section. And there is the uncertainty of an unconformity between Bhadik dolomite and Benigat slate in the central Nepal. Study 9 tried with the unconformity between these two rock sequence, but most of the section Bhadik dolomite and Benigat slate in the transitional contact. So, and uncertainty of the correlation between the Nuakot group and the Kaliganda group of the same carbonate rock unit, and the possible environment for the stromatolites. So the main objectives is mainly focused on the study of carbonate stratigraphy in the central and west central Nepal of the lesser Himalaya. The specific objects are evolutionary environment of carbonate rock and the study of stromatolites and other organ structures found in the carbonate surface, which helps to delineate the carbonate stratigraphy in the lesser Himalaya. So the methodology of the study is selection of the study area, literature review, main geological issues and the research gap, then fieldworks. In the fieldwork, systematic sampling and systematic photographs are taken, and preparation of columnar section and detailed vertical mapping. And the thin sections were prepared for the mineralogical and petrographic analysis with the help of petrography and mineralogical analysis and columnar section. Then studied position of carbonate structures and the depositional environment can be detected, and then conclusion and then conclusion. So the result and discussion parts. In the molecule section, this is the vertical mapping of the molecule area, and mainly there are 4 carbonate bands found in the molecule section. Upper part of the North formation, Dharin dolomite, and Jiku carbonate, Jiku bed of the Benigat slate, and the molecular limestone in the molecule section. So in the North formation, mainly there is the intercalation of the thin bedded thin white to blue dolomite with laminated gray to blue phyllite in the upper section in the North formation, and then these carbonate bands are increasing in the north side, upward part of the North formation. So Bhadik dolomite contains the laminated to thin bedded grey sandy dolomite with iron leaching in the area, and the stromatolites are found in the Bhadik dolomite. So in the mainly middle part and lower middle part of the Bhadik dolomite contains the stromatolites. Dome-shaped stromatolites are found here. So this is the photographs of the dolomite in the molecule section, presently in the Dharin dolomite, and the photomicrograph shows the quartz, dolomite, microsphere, and the wavy organ map with bottom portion proceed carbonaceous clay, and the upper portion possess the rainbow color due to the alteration of the line mode that can be seen in the microphotographs. So the Benigat slates is transitionally contact with molecular limestone, and it is difficult to find the unconformity with Bhadik dolomite in that section, and other section I found the transitional contact between the Bhadik dolomite and the Benigat slate. And in the Benigat slate, upper part of the Benigat slate, there is a carbonate band that is called the Jiku carbonate beds, and that carbonate constitutes the microlaminated texture. Next. So, molecular limestone mainly consists of thin to thick bedded siliceous limestone with phyllite party, and In the molecular limestone, the middle portion consists of stromatolites, and the morphology of the stromatolites is different from the other carbonate bands. So this is the stromatolites present in the molecular limestone, and in this region the morphology of the dolomite is different than the Dharin dolomite, and the concave crested stromatolite is present in this carbonate area. So this shows the cyclic pattern visible in the ecosystem fluctuation of the carbonate sediments of every units in the central Nepal molecule area. So say similar type. So this slide is the distribution of the carbonate constituents throughout the whole carbonate band in the molecular area, and left one is the correlation of carbonate ring of the study area with the standard developed by the Sturgeon and Battrai. Sturgeon and Battrai put the unconformity between the Dharin dolomite and Benigard slate, but till now I didn't find the sign of unconformity over there. So the carbonate constitutions different. In Dharin dolomite, more carbonate, that is calcite is more than other carbonate units. So this is the petrographical analysis on the mineral composition in the carbonate area, carbonate rocks of the molecular section, and it helps to classify the carbonate rocks detailing from that section. So in the Sanja section, this is the geological map of the Sanja section. And here mainly is the Anpuri limestones, river member of the Soric formation, Dharin dolomite, and the Northwood formation contains the carbonate band. So the normal formation. So in this section also the similar type of the lithology is found in the Northwood formation. The upper part consists of the carbonate band, which is pink quartzite is intercalated with dolomite. So in the Dharin dolomite, the transitionally Dharin dolomite is transitionally contacted with the Benigard slate in this section also, and columnar section shows the in the bottom part of the Dharin dolomite dome shaped stromatolites is present, and in the upper part of the Dharin dolomite also the stromatolite is present in this section.
4 minutes remaining.
So dome or the of colonia stromatolites observed in the lower middle section of the Dharin dolomite, and the colonia stromatolites of the Dharin dolomite indicating the growth and pseudocolumn columns in this top region. It is the classification is based on the Pomar, and it is similar to the colonia Pomar stromatolites in Dharin dolomite in the Sanja section. So Soric formation, the colonia columnaris dolomite is present in the carbonate band of the Soric formation. So in the Anpuri limestone is a typical type of the lithology, that is parallel limestone. In the blue-grey limestone is present in the Anpuri limestone, and there is no any significance of the organics is found in Anpuri limestone. So in the liquid formation, the highly siliceous dolomite is present, and it is transitionally contacted with the Chapani formation. So Chapani formation are the dolomite Chapani formation, and in the top part of the Chapani formation, the dolomite consists of the transitional contact of Chapani formation, and it also contains the dolomite, static form stromatolites, and static fera stromatolites, and stencharia, coral leaf stromatolites is found in this subsection. So it is difficult to correlate the carbonate band with the stromatolites in our university. So Theravadi formation consists of nodular type stromatolites, that is Caniscolabia type stromatolites in the middle portion of the Theravadi formation, and Turkey dolomites are also found in the Theravadi formation.
You have 1 minute remaining.
So this is the correlation chart of lesser Himalayan rocks in the western and the central Nepal. And it is very difficult to correlate the Theravadi formation with the rocks found in the Sangha section and the other carbonate units. Mainly correlation is done on the basis of the stromatolites found in the rocks. So it is due to the according to the morphology and their types of the stromatolites, it is difficult to correlate the carbonate bands of the units. So this is the correlation schemes, similar types of the correlation scheme. I try to correlate these different sections with the standard stratigraphy units developed by the Stopping and track. So these are the compositional distribution of the minerals found in the carbonate rocks. It helps to classify the carbonate bands. Next slide, please. Similar practice. So in the conclusion, there are several prominent carbonate bands included in the upper part of the North Pole Formation, having dolomite, the carbonate member of the Geological slate, and the molecular limestone in the central Nepal. And in the Palpa section, mainly Chapani formation, Variety formation, Soil formation, and Theravadi limestones contains the carbonate bands. And additionally, recovery member of the soil formation and Anture limestones are found in the Sangha section. And the molecular limestone contains conophyton stromatolites, shows that molecular limestone deposited in the Precambrian to Cambrian boundary according to the UI. And nodular stromatolites observed in the Theravadi formation, and it helps to correlate the molecular limestone and Theravadi formation at the same depositional environment. And there is not other sufficient evidence to correlate the Theravadi formation with the other rock types in the Sangha section and the other section. Thank you.
Thank you, Vasanta Devgupta, for your presentation. Now, floor is open for question and answer. We can take only 2 or 3 questions, please. So we don't have any questions. The next speaker is Sunil Lamsal, and the title of his presentation is Stratigraphy of Tongas and Nivan area, section of Western Nepal.
Today I am going to present my research with the title of Stratigraphy of Tongas Nivan section of Western Nepal. Here is my general outline for the presentation. Firstly, the introduction part. From the map of Nepal, the green polygon is generally focused for my study, and for this presentation, I have done some vertical mapping or the columnar section development from different sections and attempt to correlate them with each other. This red line is from Longkhola section from the Bhutan district, and another one is from Tongas area from Gulmi district, and this small section from the Tanau, Count Clipper, and this is from Central Nepal Maliku Khola section, and this map is redrawn after Fuchs, Sharma, and Upredi, and from this map we can see different approach for the mapping, including lesser Himalayan metasedimentary sequence along with lesser Himalayan crystalline, showing two different lithological units defined as Chorzari Formation and Hawang Formation from Western Nepal, defined by various authors previously, and I am trying to recount this strata. Okay, this line is marked to define that this section is I have mapped and prepared a columnar section by observing mostly from the field evidences, and another one from Lungkhola section from Bhutan district, and another incline section. And for the revision, this is a different stratigraphic scheme by various authors for the metasedimentary sequence or the lesser Himalayan sequence, and similarly, this is a stratigraphic scheme defined by various researchers, and I am trying to elevate for the stratigraphy based on a development of this vertical section. So, the main objective is to clarify the stratigraphic correlation and tectonic framework of the central and western lesser Himalayan crystalline series through lithostratigraphy and structural analysis. Generally, my work is focused on field data and some sort of thin section analysis. Moving to the result section, for the lesser Himalayan metasedimentary sequence, I have reported some sequence defined earlier by other authors. Generally, a Belligard slate. Three different sections are drawn from three different locations. First one is from the Lungkhola section, Bhutan district, western part of my study, and second one is from eastern part of my study, and third one is a well-known section from central Nepal, that is Maliku section. And this shows the almost similar compositional and lithological similarities with Belligard slate from Maliku area to the slate and limestone sequence of the study area. Similarly, the Tomgas dolomite, I have named this as Tomgas dolomite since there is not such a mapping for this unit till the date, and attempt to correlate this with Maliku limestone from the central Nepal. And this shows similarities with the carbonate succession and some sort of stromatolitic structures. There is some confusion that the eastern part of the study area composed of the dolomitic succession, but when traveling, moving to the western part, the facies is altered to the limestone dominant strata, but the stratigraphic position is same. So until the day, now I have just named as Tomgas dolomite, but it may be a Tomgas formation in the final observation. Similarly, the other angle sequence study area is marked as the Resinga formation, which is correlable with the Rovac formation from the Maliku area with a similar lithotype. And this Vastu formation is a carbonate with a crystalline marble, which is not so well reported from the central Nepal. Since the Maliku section is stratigraphy is the metasedimentary sequence is terminated with the Rovac formation, and the Mavra thrust brings the lesser Himalayan crystalline sequence. But in my section, there is a presence of a carbonate marble, mostly limestone marble and some sort of dolomite marble as a facies variation. But this type of succession can be is reported from the County of Tamil district by Boda 2014, and I have tried to correlate this strata with that sequence. Similarly, another strata of quartzite, laminated bedded quartzite, marked as Purkot of formation from my study area, which is also not reported till the date from the central Nepal, but this kind of strata is reported from the country from Tanu. So this sequence is also attempt to correlate from that area. These are some photographs of that quartzite sequence from the area and the photo micrographs. Then another sequence, well-known, well-established litho unit, that is Geological formation, which is supposed to be equivalent with Radua from the central Nepal. And this unit is well developed in central Nepal, in Kau Klipe from Tano, and in our study area as well, which is composed of the garnet schist along with some sort of quartzite and some igneous intrusion as well. And these are the granite body and epiphyllite body from the Geological formation from the study area. Then the Thavan formation is the carbonate marble sequence, which is supposed to equivalent with the Vaishyadevan from the central Nepal. And for the delineating the thrust boundary, I have traversed along possible shear zone area and marked some major pointed and defined that the zone is a thrust which separates the lower metasedimentary sequence with upper crystalline unit. Here are some field evidence along with the micrographic evidence, photomicrographic evidence, demarking some shear sense indicators. This is stratigraphic correlation with Central Nepal, Maleko, Vaitadi group on the far western region, and this correlation chart is help to define the correlation with different from the study area. We have defined two new. We have tried to define the two new units defined as Bosco marble and Purkot formation. Eastern thrust like Kathmandu Nepal. Till the date, this sequence are not observed. So from the study, this conclusion can be delineate that for the after allocated sequence modification of previous lithostratigraphic classification can be suggested that the garnet is for the both area are the marker horizon and which is equivalent to the Radua as well as Radua formation from the central Nepal, and the older strata is well established for the yogurt strata is well established yogurt in the Radua and Vaishnavan. But the older than that, the two marble sequence and the quartzite sequence has to be studied and reclassified as a different unit. Similarly, different gneissic intrusion and igneous body are reported, and this is also the major. This can be also the major indication and evidences for further analysis. Okay, thank you.
Thank you so much for your nice presentation. The floor is open for question and answer. So I'd like to hand over the mic to our chair.
Speaker will be Professor Rainer Klemp, authored by Tian Yu and Zhen Yu, entitled Two Phases of Post-Onset Collision Architectic Magnetism in the Southern Lhasa subterranean Tibet, geodynamic and mathematic implications.
Michael, can you hear me? Perfect, so I do not need that. Okay, my name is Rainer Klemmt, and I'm here actually introducing my PhD student here in Lu from Erlangen University. And I will take you right now to Tibet, just for a short time, then we go back to Nepal. So if you want to, let's go to Tibet. And I'll just give you a short introduction of what I'm going to talk about. Very shortly, India-Asia collision. Then I'm going to talk about post-collision allocating magnetism and the Ganges. I'm presenting a case study in order to introduce the porphyry copper mineralization. We all know there are big, giant deposits over there, and I'm trying to elaborate why they are there. So shortly to the collision initiation between the Indian and Asian continent ages was between about 55 and 53 million years, followed by tectonic transition due to the Neothesan slab breakoff at about 50 million years, probably accompanied by slab steepening and rollback. And that was followed by slab breakoff induced between 50 and 40 million years. And you can see here, this is the result, the magmatic flare-ups between that time and the Ganges belt. Okay, I'm going to talk, as already pointed out, about edekites. Edekite rock characteristics are, as most of you know, high SiO2 content, high aluminium, very low magnesium, ytterbium, and yttrium, and high strontium. So the strontium, ytterbium, yttrium values are usually extremely high. Coming to the post-collision magmatic rocks, in the southern Lhasa subterrane, we can see in the strontium yttrium versus yttrium and lanthanum ytterbium, where those ytterbium diagrams, that almost all of the magmatic rocks display adacitic geochemical characteristics. In the normal arc magmatic field, there are hardly any rocks, not any rocks. So I know many of you and our colleagues doubt that the adacitic rock petrogenesis is unique. There are several models like partial melting of young and hot oceanic crust, the initial term, then fractionalization of hydrous basaltic magma can create these characteristics, or partial melting of upper metasomatized mantle. All of them can create adacitic geochemical characteristics. However, the partial melting of thickened lower mafic crust is the one which is preferred by almost all workers in Chinese Tibet, and it's also my preferred model. And this is favored for the two phases of post-onset collision of edekite rocks in the Ganges belt of the southern Lhasa subterrane, which we see here. Here's the Himalaya terrain, Lhasa subterranean. You can see here all these adacitic rocks in the southern Lhasa subterranean, distributing all over there. And we've got two phases, which I like to explain right now. So all of these rocks have an age of less than 40 million years. And they're distributed along the southern Lhasa subterranean. And only those ones in the east are associated with porphyry copper mineralization. In the west, is next to nothing. So why do I speak of two phases? And I show you the compared zircon geochronology. And this geochronology shows you two phases. The early phase from 38 to 25 million years here in blue, and the late phase between 20 and 10 million years here in green. You can see it also on the map. The one is in the east, and the other one is distributed almost all over the subterranean. There's also a difference in geochemistry. You can see here the lanthanum-samarium ratio of the early phase is always higher than the late phase, which is pointed out in this diagram. Lanthanum-samarium above rubidium strontium. Okay, if we have got these geochronological differences as well as geochemical differences, then we have a look at the epsilon hafnium values and the uranium lead zircon ages, and you can see immediately, okay, there are two different independent trends of both phases. And that would imply different geodynamic settings. And this is what we'll see here in the next slide, the geodynamic setting of the early phase ediacatic rocks. They show crustal shortening and thickening, and what asthenosphere was upwelling during the ongoing northward subduction of the Indian plate after the breakup of the Neothecian oceanic slab. The late phase ediacatic rocks between 20 and 10 million years were associated also with upwelling hot asthenosphere, but with extension instead of shortening and thickening, because we had the tearing or delimitation of the subducting Indian plate at about 70 to 100 kilometers depth. This is what you see here. So coming now to the porphyry copper deposits, and I'm going to elaborate on the Miocene porphyry copper deposit in the southern lava terrain. And this is what I mean. You see them here. This again is the southern lava subterrane, and I'm going to show you this area now. Oh, too fast. This area now, because this area contains the giant, big porphyry copper deposits. There's nothing in that area, in the western part of the Ganges belt. And the difference is, one of the main differences is, we've got here in the western part a juvenile-dominated sulfide deficient lower crust. And in this area, we've got a source dominated by old continental crust with sulfide accumulations at its base. So, that means, or most of my Chinese colleagues, and myself too, interpreted this is due to remelting of the lower crustal sulfide bearing copper which accumulates, and that led not only to the formation of the arachitic rocks, but also of the porphyry copper deposits, especially the giant porphyry copper deposits. Sorry. However, this is where my group comes into this game. Little is known concerning the magma differentiation following, subsequent to the formation of these ediacatic rocks. And thus, the actual mechanism of the metallogenesis is not really that well known. So you're going to say, so what? We know where the porphyry copper is. But it is important because we have a look at that area again, and you can see here maybe the squares associated with the porphyry copper deposits. Because every porphyry copper deposit is associated with ediacites, but not every ediacite is associated with a porphyry copper deposit. And this is why I introduced it to you in a case study. Here you can see this. That area, this is the so-called Naomo composite pluton of the Ganges belt, intruded at about 50 million years ago. And in this composite pluton, we had ediacatic intrusions. We had the early phase in the south, and we had a late phase in the north. And the late phase contains exclusively the Miocene porphyry copper deposits. So we are in that area. You can see here the early phase, and only the younger phase is associated with the porphyry copper deposits. Try to study this, the geochemistry via zircon geochemistry. And you can see here the European anomaly, the proxy against zircon hafnium, and it shows us that we are actually dealing with an area of about 70 kilometer thickness for both phases of anechites. The early phase, which is more monster granite, and the other ones, the late phase is granite dioritic. Both come from about 70 kilometers depth. Similar. However, if we have a look at the thorium-uranium ratio, again against zircon-hafnium, you can see that the late phase, the granodiorites, have a higher ratio, always a higher ratio, than here in blue, the early phase. Now that's very typical for magmas derived from extensional settings, which always have higher zircon, thorium, uranium ratios than those in compressional settings. Having a look at some of the ratios, in particular the uranium-deuterium ratio against hafnium, you can see the uranium-deuterium ratios increase with decreasing as zirconium-hafnium, indicating crystal fractionation, while especially seeing the almost constant partition coefficients, while the late phase associated with the porphyry copper deposits are almost homogeneous, showing equilibrium crystallization. We also did some modeling, thermodynamic modeling, with estimated pressure and temperature. As you can see here, we could nicely model the early phase with fractional crystallization. As a second phase, again, equilibrium mineralization. So, coming to my last slide, we also wanted to know what's the difference when it comes down, and that's very important, the oxygen fugacity. Do we have a reduced or an oxidizing magma? As you can see here, if we have a look at the magmatic oxidation state derived by zircon-cerium ratios, you can see that this ratio decreases with increasing hafnium, implying magnetite fractionation. What's left, the melt left, in other words, is reduced in its oxygen fugacity. We have again same ratio against hafnium from the late phase. And again we see it's relatively constant. So our interpretation of the geochemistry would be that, and the modeling of these magmas would be that progressively reduced oxygen fugacity conditions during magnetite fractionation in the early phase magmas resulted in sulfur segregation from the melt. So the melt had no more copper or other molybdenum metals left. And during equilibrium crystallization, the magmas formed had high oxygen fugacities in order suppressing sulfur segregation and forming CO2-rich anakitic rocks in the Genghis magmatic belt. Thank you very much.
Thank you. I have a few questions. Pre-collisional biotite, hornblende, granite diorite tailites all the way along. So why do you only get porphyry coppers in the east and not in the west? Do you not get any apatites in the west?
Look, I had 12 minutes, 30 minutes, so I couldn't give you the full story. Okay. But there are porphyry coppers deposits in the west, but they are all Jurassic. And in the east, there are no Jurassic ones. So one explanation is, I think the thing, it's already gone, otherwise I could show you. I prepared, although I nearly guessed you would ask me that question, so there is a slide prepared. But the thing is, the dip of the Indian lithosphere to the west was very shallow, the angle. In the east, it was completely ripped off, you know, all these northeast faults. And this is why you had, from the shallow magma, and not the steep dipping one, you had the production during the Jurassic of oxidizing magmas. So you had there, at that stage, you had porphyry copper deposits of Jurassic age. In the east, you had none. So, in other words, you at that stage reducing magmas forming sulfides in the lower crust, which were remelted. Couldn't remelt in the west because they formed already during Jurassic times. That's one of the stories. It's not everything. The Canberra school is of the opinion that this is not the full story. They rather think that the mineralization is exclusively associated with these big faultings. But not all faults contain actually porphyry coppers. So that can't be the answer either.
The porphyry coppers are all Miocene in age in the east, is that right?
Yes, well, they are big, giant deposits.
Most of the Ganges Ladakh granites in the west are all pre-collisional, and there's very, very few adikites and no shoshonetic magmatism.
They didn't find anything yet, but what's always wondering why I came the first, 4 years ago or 3 years ago to Nepal. I wanted to actually collect some of the adikites. But the people from the survey here, I asked them, they didn't even know adikites. Because I wanted to use some exploration tool.
They're all in Tibet.
Okay, now time to move on.
Okay.
Next speaker. Navaraj Paraduri. A thick quartzite succession in the last Himalaya of Pokhara, Bagram area, different from us. Implication for the geography of the Kuncha Formation.
I'm here to present my talk on a topic quartzite succession in the lesser Himalaya Pokhara Bagram area, implication for stratigraphy of Kuncha Formation. So I would like to directly move to my site location, study area. It is mainly located in the Pokhara Bagram region and consists part of lesser Himalaya. This was the earlier map prepared by Frank and Crow in 1970. Here we can see the region between Pokhara, Bagram and some part of Sangla and Parvat are mentioned as map. There is no any succession of quartzites or other units. They have just illustrated it as a map, and the composition mainly consists of schist, phyllite, quartzite and other black phyllites and slates. This is the map from Kolsai. So the important thing about this map is he has mentioned Birethati quartzite as the oldest unit of lesser Himalaya. So now I would like to move to the stratigraphic columnar section of Stockley. Here he has mentioned that in Kuncha Formation there are various units, various members of quartzite units. He has mentioned Panchpani quartzite member, which thickness is about 200 meters, and he has also mentioned that there are other quartzite members within the Kuncha Formation. These kinds of quartzites have not been noticed in the study area. So this is the map prepared by Department of Mine and Geology. The good thing about this map is that they have separated different formations. They have like separated quartzites in different formations. They have named Ranimata formation as the oldest, Kusma formation as the youngest, then Ranimata, and the most youngest quartzite as Naurada formation. Now I would like to move to the investigated area geological map. Sorry. So this is the other map mapped by Central Department of Geology, and the region of my study area is here. So here they have mentioned that there is. So this is the recent map that we have developed. Here we have find out that the quartzites that were mapped earlier by Department of Geology and other researchers, they are the single units, and there are lots of structures, major structures such as anticline and syncline. In the previous map, it was mentioned that there was synclinal antiform over here, which was mentioned to be overturned. But in our recent study, there is no any such evidence, and we have mainly focused on the primary sedimentary structures to perform this study. So here we have like within the Kuncha Formation, we have different quartzite units, and we have like older phyllite units consisting of phyllite and meta-sandstone. The upper part is the quartzite, and the younger is again the phyllite and meta-sandstone. The quartzite, the middle part of the Kuncha formation, is mainly composed of phyllite and amphibolite bands. So this is the recent geological map that we have investigated. So here I would like to show you the cross section from this line AB. There you can see different anticline and synform structures. There is also polyvas thrust at the south of the study area. I would like to move to some field photographs. So these are some of the primary sedimentary structures that we have observed during our field study. So these are some of the folds, major folds, some of the overturned beds over here on the bottom right side picture. So we have like crossed sequence, cross zones over this region. These are some of the folding structures that we have observed within the Kuncha formation of our study area. Okay, so I would like to move to the conclusion. In West Nepal, the Kuncha formation consists of thick quartzite succession outcropping between Pokhara, Sangha, Polyvas, Kusma and Parno. The stratigraphic criteria from the investigated area reveals that there are a few quartzite beds within Kuncha formation, and their thickness varies from few hundred meters to more than a kilometer. Previously named lower quartzite, Viretati quartzite, Naudana quartzite, and Kusma quartzite, as mentioned by Department of Mine and Geology, Fuchs and Franks, they have been, they are, from our study we have named them as a single unit within the Kuncha formation, and that differs completely from that of Fakfok formation. There are quartzites similar in nature to the Fakfok sedimentary structure, but we can say them that this is the Fakfok quartzite. And the other ripple marks, cross-lamination, graded bedding, indicate primarily a right way of succession. So what I would like to say is that the previous made geological map of the investigated area need to be revised, and few of them are the best, like Paulsen, where he has shown the different lithostratigraphic units, stratigraphical units from south to north, mentioning from Kuncha to other dolomitic units or quartzite beds at the top. Thank you.
Thank you very much, Dr. Palachuri. Any question?
We have a lot of zircon datings done in these areas. Do you have that publication? That would be very interesting for you. Martin.
Dr. Martin.
Yeah, okay. Around Martin and others.
There was research at that area conducted by Professor Lalu Todal as well.
No, for zircon dating I'm talking about. A lot of datings are there. If you need, I can share the publication to you.
Okay, thank you so much.
Good to hear that Aaron. Oh.
My question to Nagaraj is, because you talked about the quartzite, the thick succession quartzite units in your study area, why these quartzite units are not equivalent to Fakfok quartzite when you compare to the central Nepal? So can you see the stratigraphic column so that your quartzite units lie within the Kuncha formation? How can you support these field evidences?
Okay, so when we map the area, we found that the quartzites are basically within the phyllites. When we look at the stratigraphy, after the Kuncha formation, there should be like.
Do you have this stratigraphic?
No, I haven't presented that stratigraphic columnar section here, but during the paper I will definitely have.
Hello. Did you find any evidence on Kusma fault? I also carried out storage mapping of that area for one storage project, and found the evidence of the Kusma fault.
Kusma fault. Yeah. So we have in my map that I have presented, we have like polyvas thrust over there.
Polyvas thrust, I know is.
You are talking the thrust fault on the northern part from the polyvas thrust, right?
I forgot it. Polyvas thrust separate my account and northern formation. So this Kusma fault which I am talking, this thrust repeat Kuncha formation and Fakfok. formation like?
So in our research investigation, we don't have such kind of faults. We have rather one unit, quartzite unit within the Puncha formation.
Thank you very much, Dr. Parajuri.
So I'm Malay Mukul. I'm from Indian Institute of Technology in Bombay. And thank you for giving me this opportunity to present the talk here. And these are my co-authors. So these are my co-authors. This is Dinesh Srivastava and Manas. And in the background you can see COSI. That's a picture where we were doing RTK related GPS. Okay, this is the pointer here. There is a statement. Yeah, the COSI has undergone multiple versions. Again, you can see those dates are given here, and basically our study area was between Indo-Nepal, right at the border. COSI comes out of the Himalayas and enters Poland. So the 2008 version, if you are not familiar with that, on August 18, 2018, I don't remember the exact time, probably around 10 o'clock or midnight or early morning. COSI was flowing like so, that's the COSI fan. And overnight, it started flowing like this. Okay, so here's the original COSI, and this is after the version. The entire channel has actually shifted somewhere. And this continued till, you can see September 2, and things were pretty messed up here. You can see there are two different imageries here from Doppler flood observatory. So this avulsion was probably one of the most dramatic and very damaging avulsions. So we started looking at this particular problem, is why exactly is there any structural control on this? Next. So till then, the COSI avulsion was attributed primarily to geomorphological causes, and the thing that was recognized by geomorphologists is that COSI flows in a super elevated channel, which resulted from excessive sediment degradation, because as you all know, COSI has a very high sediment carrying load or sediment load, and because of the fact that it was moving around in its fan, there were artificial embankments that were created to keep the COSI within those banks. And the eastern embankment reached at Usaha, which is in Nepal, in 2008, as the river was flowing along the eastern embankment. And one of the things that was recognized was that there was also effect of some lateral slope across the channel. So all of this came out of geomorphology, and they also suggest that the COSI barrage may have actually reduced the down valley slope or the down river slope and influenced the entire process. But when we started looking at it next, so before we started looking at the overall COSI frontal problem, this is the structural setting of the COSI. And as Mary was talking earlier this afternoon, so we have the structure here that sticks out, which is named as the Dharan salient. And on either side of that, you have some kind of a transverse structure. Here, we actually have a fault, which has been mapped in the field by us, and the geology across it is completely different. Here, the modern front is not defined by MFT, but by rounder thrust. And here, of course, we have the usual MFT. In the Indian part of Dharan salient, we actually have a briquette fan, whereas here there are some faults being mapped by Italjio, but I'm not completely sure if you saw a lot of briquette fans. But what happens is, once you cross over COSI, you go from east bank to west bank, the MFT is basically way down here. Okay? So there is a dramatic change in the geology across Australia. So this practically tells you that there has to be some kind of a transverse structure here, which Mary has actually gone and looked at and found traces of this structure. But this needs to be worked out in much more detail on exactly what's going on here. It also leads to the problem that how is, if there's a lateral structure here, how is it affecting the exit? Next. So if I just zoom to the western part of the Bharan salient, you have inner Chudia range, which is defined by Marine-Kola thrust and Manula Kawa thrust. And the frontal part, which is outer Chudia range, which is this part, is related to main frontal thrust. And that has frontal antiforms from the paper by Acharya et al. In 2020. And so they have related this to fault bend folding, but it might not be exactly fault bend folding if we are looking into the structure in one. What you can see here is the part which is relevant to COSI. There's actually no data here from this, so this is the part that needs to be looked at more carefully. Next. So now, in this structural setting, if you look at the entire COSI fan, the other thing that comes out is you have the Munge Sarasa ridge. So this whole fan is actually developed on the Munge Sarasa ridge. If you look at the topography of this, take a cross section across this. There's a median high of the ridge, and till 1921, the COSI was actually flowing to the east of this median high, and then of course moving around east of the median high, and giving you, different tributaries or emulsions here, which showed that it varied around east of the median. In 1922, for some reason, which happened way up here, this changed to this. And then of course, when it went to the west of the median high, the structural setting also changed. Here, it was flowing completely within the Bharan salient, but as soon as it went to the west of the median high, it started interacting with the outer Chudia range topography. So then, to simplify everything, on the west, so in COSI, in the eastern bank, you don't have any such topography because the MFT is way back here. And here, because of the MFT being in front, that's a problem again. Why is it way to the front here and not here? That's a problem we need to look at. And also what's going on in this particular area, including this little topography here. Is it related to the COSI structure, or is it related to MFT? Or is it related to Kamala Toha thrust? That also needs to be looked at. But this is the setting, and wherever the 2008 beach occurred, the Mahuli antiform, which is on the eastern side of this outer Chudia range, basically traces right into the area where the beach has occurred. So to actually look at this in more detail, we did topographic surveys in this area, which is the soft area here. And you can see the red ones are all RTK GNSS profiles, and all numbered ones are essentially your SRTM data which has been corrected. SRTM data, if you use it as is, has lots of errors. So by using this RTK base stations, or as ground truth, we corrected all the SRTM data in this region and started looking at this problem. Next. So here is the base station being set up, the field, and that's COSI. We did a boat survey right through the river as well as different fields. So that's called the base station. These are rovers. So you move this around and actually correct the Next. So what we found is there was very pronounced northwest southeast slope on the west bank of COSI. And you actually had well-developed outer Chudia basins that were flowing from west to east. So whatever was going on here, definitely the COSI was not. And actually, if you take a soft profile of the topography, you can see that there's a very pronounced slope from west to east. In 1986, it was here. Then 1989, it was here. 2003, it was here.
and then a version occurred, and artificially that has now been established with flowing here. So gradually it was also moving laterally downslope due to this natural slope before the version occurred. And because of this, it was right next to the eastern line. Next. If you also look at channel elevation versus floodplain elevation of western floodplain and eastern floodplain, what you see is it's mostly positive here, mostly negative here. So channel elevation is larger, except for a small region here. But in the eastern floodplain, most of it, the channel is far more elevated compared to the eastern floodplain. And you can see CS07 is where approximately the version 2008 version occurred. We calculate version indices. There are various indices calculated by different people. They also seem to be highest here in the degree away from CS07 and CS08. If you just look at the cross valley slope versus down valley slope, then the highest ratios. Then this is the result of the boat survey, which we essentially did from that's your survey which we did across the barrage. You can see here that the elevation and the slope basically varies or occurs in a region which is influenced by a structurally controlled MFT related topography on its west bank. And this is completely absent in this east bank. This could be a cross fault or some kind of a transverse structure that we need to look at more carefully. And the Kosi channel is super elevated asymmetrically, not symmetrically like you see most rivers in super elevate and pulse, and that's only or dominantly respect to its east bank. And the structural and topographic setting of Himalayan river exits, in addition to river geomorphology, should be looked at to give better insights into river erosion. Next. So, providence, this work was possible with the help of site engineers and staff at Kosi Barrage, and also Nepalese authorities in the Kosi Tapu region. And the RTK data collection will involve students from IIT Bombay and IIT Kanpur. Next. Thank you for your time and attention. This is Kosi, and if you want to see details of this work, it was published.
Thank you, Professor Foucault. Is there any question? I was curious to just to know these big earthquakes, let's say 1934 earthquake, if that has really, well, there are some controversies, but if the MFT has really, has been active at that time, do you have any relation to the channel flow with the large earthquakes like 1934? Is there any evidence of such kind of thing of 1934?
I mean, earthquakes, if they are thrust, they should basically increase the topographic slope, or in the worst case scenario, like Allahabad, in touch, block rivers, which happened in the matter of hours. In this case, whether I see that or not, nothing yet. We are still looking at it. We still have to understand why the structure transitions across the Kosi River so dramatically. And especially if you actually look at just the Google Earth map like Mary was doing, you can see that the MFT makes a necklace kind of a structure in the Trijagal loop. So now that necklace kind of structure can occur due to various structures. One of them could be this rejoining splay. Other can be there are two transverse structures which are basically bending the fault into it. So these are aspects which we need to do much more careful work. And we've been trying to go there, with Mary and other people here, but so far we've done very limited work. But yes, I mean, if you find evidence, neotectonic evidence of terraces which date to 1934, theoretically yes, that's what it should do, but we don't have any evidence here.
What is a specific structural feature you identify controlling Kosi River? How do that feature interact with fluvial process? in Kosi River erosion in Nepal Himal?
One specific structure, I suspect there are more than one structure. Okay, so right now we can see that there's an antiform, frontal antiform, which is fault related. It may be fault vent fault, fault propagation fault. That seems to actually create the slope which is affecting the Kosi. Okay, so the fault, that slope, the topographic slope which is affecting the Kosi, which is northeast to northwest to southeast, that's structurally controlled. Now, whether it's only controlled by MFT, or even there's a cross structure that is affecting it, or by MFT and the fold and the cross structure, that's a question which we are still working on. Okay, so, but there is definitely some structural control. Exactly one structure or multiple, that I cannot say.
Thank you very much again, Professor Muku, and I will invite my co-chair for closing statement.
Thank you, Chair. So talking about the concluding this session, this was the third technical session of the day. We had total 6 presentations, including one special paper by Professor Nariava. Papers were related to geomorphology, stratigraphy, paleontology, and mostly tectonics, as well as immobilization. So I would like to express my gratitude to all the presenters for such a nice presentation. And let's have a big round of applause for all the presenters. At the end of the session, I would like to thank NGS and for providing all of us this opportunity to appreciate. And my special thanks goes for our chair and director, Professor Chair. Thank you very much.
To continue the program, now I would like to request our convener, Mr. Professor Gupprasad Koren. Similarly, token of appreciation for co-chairperson Monica Chan. And rapporteur for the session, Mr. Prakash Mittal.